Hello, everyone. We're going to start chapter 13 in this video, and this will be kind of a start of some new ideas for us. I kind of prefaced this course at the beginning with some kind of introduction video where I talked about chapter 12 is kind of building up the building blocks of this higher dimensional space, these higher dimensional spaces like R3. And just learning how to work in that space. And then we're going to start learning about functions in that context. So that's kind of where we're at. So again, to kind of reiterate what's going on, in Calc 1 and 2, we saw functions of this form, right? We saw functions of a single variable. Okay, what does that mean? It means our input was a number and our output was a number, okay? So that's what this notation means. When you see notation like this is the domain or the inputs, and this would be the codomain, or maybe you're more familiar with the term range. Bit of a distinction there, but it's not important. And we can think of this as the output, right? So what this is saying is, okay, our domain here is all real numbers, and our codomain where our output is somewhere in the real numbers as well. And we often wrote fx equals y, right? So that was our independent variable or dependent variable. In other words, our input and our output. So if you look past the fancy words, this is what we're used to. Okay. Now, there's a lot of, this is what we're used to, but there's a lot of other ways we could, a lot of other forms of functions we might see. Okay, so these are some of them. Okay, so let's say I'm looking at this function on top. It's a function R from the real numbers to Rn, right? Where this is n-dimensional space. So we're going to deal with this in this section, and usually this n is going to be 3. Okay, so when I write n, that just means, okay, we're not being specific about what dimension we're in. Okay, but usually it's going to be 3. Okay, so this is a function whose input is a single number and whose output is a point or a vector in R3. Okay. Now we could also see kind of the reverse of that, where, okay, I have a function s from Rm to R, meaning my input is a vector in some m-dimensional space, and my output is just a real number. Okay. And then the most general, maybe the most general way to deal with functions is when I'm starting with a vector or a point in m-dimensional space, and my function sends it to a point in n-dimensional space. Okay. Again, in this chapter, we're going to be pretty much exclusively concerned with this top case, R to R3. Or if we want to think about it more generally, R to Rn. And then in chapter 4, so we're going to do this first, and then in chapter 14, we're going to be considering this. And then in this course, we don't really consider this third case too much. Okay. So again, we're going to be dealing with scalar input, vector output. Now, it's nice to start with this because that first case is a bit easier than that second case. Now, since just a little bit more terminology, when I have this vector R from the real numbers to this R3, or more generally Rn, the output is going to be a vector, right? The value of the function is going to be a vector. So creatively enough, we call a function like this a vector-valued function. Okay, so when you see the term vector-valued function, just think, okay, the output is going to be a vector. Okay, so now we can review a little terminology. So usually how we're going to see this written, instead of seeing, remember we're talking about R talking about a function like this, r to rn. And maybe sometimes to make it clear our output's a vector, maybe we'll write it like this. Now, instead of writing, when we were doing our usual thing from r to r, I wrote f of x equals y, right? Well, instead of writing f of x, I'm going to be writing r of t. Okay. So that this is just my function, and then I'm plugging t into that function, and t is just some number, some scalar. Now, as I said before, the dimension of our output is usually specified when I'm defining these functions, right? Usually, I'll be defining a function and I'll write it like this, r to r3. Okay, so I know my output's going to be in r3. When we're talking about things generally, we might just leave it as n for the nth dimension. But as I said, we mostly care about r3. So this vector valued function, right? Again, we're used to writing f of x equals y, right? Well, instead of writing f of x equals y for these vector valued functions, we often write this vector r of t equals a vector, and then this vector has components r1, r2, r3. So that's what we've written here, same thing. Now, since this vector here is a function of my t, right? This vector and all of its components depend on this number t. Okay, so in some way, this r1, we have to be able to write that in terms of t somehow. And same thing with r2 and r3. So we can actually be a bit more specific. We can say, okay, this vector, this vector valued function, we can write that as a vector whose components are f of t, g of t, h of t. And now each of these functions in these spots, these are all just our normal idea of a function from real numbers to real numbers. Okay, so these f, g, and h functions. They're the same thing we've seen in Calc 1 and Calc 2. They just take t as input, and they give a scalar or a real number as output. And then we take that output and we plug them into the spots here. And when we plug in those three numbers into those three spots, we end up with a vector. Now since these functions are giving us the components of our vectors, we call them component functions of our vector r, or of r of t. Okay, so let's see some quick examples of these vector valued functions. So maybe r of t is defined like this, okay, where on the right side I have this vector, and what are the components of the vector? Well, the first component is always 0 for this example, the second component is t, and then the third component is 3 minus t. Okay, so that's one you might see. Another one, which we're going to deal with a couple times in this section, r of t is equal to sine of t, cosine of t, and t. Or we might start seeing something, some stuff more complicated like this. They're all vector valued functions. The important thing is that these vector valued functions, I could think of them as being just completely defined by their components, right? So if it helps, this vector valued function, just think of it as three of our normal functions inside of vector. Now, just like with our functions from Calc 1 and Calc 2, something like this, we talked about when we were looking at these functions, we talked about we talked about limits of these functions, continuity, derivatives, integrals, and so on. So those are the kind of four big topics for a function of a single variable, right? And we're going to talk about limits and we're going to talk about all these topics really for these functions, for these vector valued functions. In this section, we're going to start with limits and continuity, and the limits and continuity for these vector valued functions are pretty easy. It's just a very slight adjustment from Calc 1 and 2 to this material. Differentiation, integration maybe takes a bit more of an adjustment, which is why we'll cover it a bit later. But in this section, we should just be able to cover these limits and continuity really quickly. So let's talk about limits first, because we can't do continuity without limits, right? Okay, so hopefully you guys are, still remember some of the basics about talking about limits of functions. It works really simply. If I have, let's say I have this vector valued function, okay, where it's got components f of t, g of t, h of t. Just like with functions of a single real variable, I might be concerned with what the limit of this vector valued function is as t approaches some certain value. Okay, so let's consider the limit as t approaches t sub 0 of rt. Okay, what's happening to these vectors as t gets closer and closer to t0? So I'm plugging t's into here. I'm getting points in R3, vectors in R3. And as t gets closer and closer to t0, what's happening? What's that limit? Well, it turns out the limit is really easy to compute. I just take this limit inside my components, and that's going to give me the limit of my vectors. Okay, so it works out very nicely. It kind of works out how you would hope, that basically if I see limit of RT, okay, I just consider the limit of the components. So we can take the limit inside the vector. So let's consider this first example. Okay, let's say R of t is defined by this vector valued function here with these components. And I want to figure out, I've kind of spoiled it here, but let's say I'm given a problem and it's telling me to compute the limit of RT. Well, how do I do that? Well, I just look at the components and I ask myself, okay, what's the limit of this first component? As t goes to 3. We're talking about the limit as t goes to 3, right? So what's this limit? Well, let's see, as t goes to 3, right? I can, since these are continuous functions, I can just plug my number into my functions, right? So basically what I do is I plug 3 in here for t, right? That only works because this is a continuous function. So the limit of this thing is what? E to the 3 times 3, so e to the 9, and then plus 7 to the 3 squared, so plus 7 times 3, or excuse me, plus 7 times 9, plus 63. All right. And now I'm looking at this second component here, okay, t. Well, what's the limit as t goes to 3 of t? Well, that's really easy, right? The limit of that thing is just 3. Again, because this is a very simple continuous function. Okay. And this, I need to change, I changed this when I was writing my notes. Let's make this 3 minus t. Now I consider the limit of this thing as t goes to 3. Okay. Well, there's a problem here. Okay, I'm looking at this third component now. this thing is not continuous at 3, right? If I plug 3 into this, I'm dividing by 0, okay? So that's bad, right? And in fact, if I plug 3 into the top, I get 0 as well. So this is a limit where I have the limit of 0 over 0, right? What does that remind you of? That's L'Hopital's rule, right? So I take the limit, I use L'Hopital's rule on this third component to compute the limit. And what do I get? Let's just focus on this now. So I compute L'Hopital's rule. Okay, and this becomes, I use L'Hopital's rule, and it becomes, let's see, negative cosine of 3 minus t over negative 1. Okay, and the limit of that as t goes to 3 is 1. Okay. So this limit in the third component is 1. Okay. And as you see here, we might have to use some of our techniques, our limit techniques from like Calc 1, the same limit techniques we learned in Calc 1 to compute these limits of these components. So I used L'Hopital's rule there. And I got the limit of that component as 1, which is what I had erased before. All right, so we've seen how to deal with limits. We just take the limit inside the vector. No big deal. And then the rest is just relying on our previous knowledge from Calc 1 and 2. Continuity. Okay, so almost always paired with limits is continuity because it's the next kind of natural step. So we're used to the idea of continuity for our normal Calc 1 and 2 functions from R to R. We have this intuitive idea that it's a continuous function is one you can draw without lifting your pencil, right? But we also had this technical definition, and this is what we need to start relying on more and more. We said f was continuous at a point x0 if the limit as x approaches x0 of fx is equal to f of x0. Okay, so that's our technical definition. And then remember, we said f was continuous, just continuous, if it's continuous at all points in its domain. Okay. So continuity is defined for points, for individual points, but let's say I have a function and it's continuous everywhere on this interval a to b. Well, how could I say, I don't want to say, well, it's continuous at that point, it's continuous at that point, it's continuous at that point. I want some kind of shorthand. So we would say f is continuous on the interval AB. And if it's continuous just on all of R, boom, on the whole real line, we would say, okay, f is continuous on R. And if it's clear what our domain is, we don't even have to mention the domain. We can just say f is continuous. Okay. So that's our idea of continuity from Calc 1 and 2. And then again, it's a pretty natural extension to this Calc 3 material. Okay, so just like with limits, we can consider the continuity of the components. We can look at the individual components inside the vector. So now I'm dealing with this function, this vector valued function from R to Rn, and we're usually going to be working in R3. So maybe I have a function like this, R of t, and then it's got its components that's equal to the vector f of t, g of t, h of t. Okay, this vector valued function is going to be continuous if all these components are continuous. Okay, and I said if and only if here because, well, that's just a technicality. You guys don't need to worry about my diction, I guess. What I want you to know is that, okay, if these components are continuous, then this, the vector valued function as a whole is continuous. And it works in reverse too. If I know the vector valued function is continuous, well, that means all these components are continuous. That's what if and only if means. It goes both directions. So going back to our previous example, we just looked at this example, right? We said we're considering the limit of this thing at t equals, let's see, we use slightly different example. Use this, right? So this was our previous example. Okay, and we noticed that, well, at 3, here I'd be dividing by 0, right? So this function's not continuous at t equals 3. Even though the limit exists, the function's not continuous because it's not defined at this point, right? We can't divide by 0. So that value is not defined at t equals 0. So the function's not continuous at t equals 3, so it's just not, the function's just not continuous. All right. Now let's look at this function. R of t equals sine of t cosine of t t. Let's look at the components, okay? And let's think about this for t, all t. Okay, t between negative infinity and infinity. Is that continuous? Is sine of t continuous? Yeah, that's always continuous, right? Okay, so sine of t is continuous. What about cosine t? Yeah, that's always continuous, no matter what the t is. And then t, is that continuous? Yeah, it's about the most basic function you can have. So that's most basic continuous function. So yeah, this is all continuous. So all the components are continuous. So R of t is continuous. And if we want to be specific, we could say it's continuous everywhere, continuous on R, etc. Okay. So continuity is defined on the space we're coming from. So this is a function from R to R3, right? So its continuity lives in here, okay? So we would say our function is continuous on R, not R3. And that's just a technical point and probably shouldn't be important for you. Now again, the more general case is more complicated, which we'll deal with that in chapter 14. But we're starting off nice and light in chapter 13. So limits and continuity are really pretty straightforward. I just look at the components. Okay. And we have to talk about limits and continuity before we can do graphing, which is what 13.1 is almost entirely concerned with. So just like functions in R, from R to R, continuity was a big thing, right? So when I'm considering a function R to R, if this function is continuous, its graph, what does continuous mean? That intuitive idea means we can draw it without lifting our pencil. So it's got, it's nice and connected. It doesn't have any ugly, jumps or discontinuity, things like that. If a function's continuous, it's got some sort of, I'll call it smoothness, although that would not be an appropriate term in mathematical context. But for intuitive purposes, these continuous functions are sort of nice and smooth, connected, and things like that. All right. So we want that same kind of property for these vector valued functions. But first, let's think about what these vector valued functions look like before we start, kind of thinking about continuity of these curves. So what does the graph of a vector valued function look like? Well, we know the input is just a number, and what's the output? The output is a vector, right? So I plug in t to my function, and I plug in t to each of these components, and I get an output in R3, right? So maybe for, R2, okay, R of 2. What vector is that going to give me? It's going to give me 2, 2, 4. Okay, so my output is this vector. Okay. Now, what do these functions look like? Well, it would be complicated to kind of draw the input and the output on the same, or give an axis for the input and 3 axes for the axes for the outputs. So let's just focus on the output for now. Let's forget about graphing the inputs, or kind of making it clear where the inputs are coming from. Let's just graph the outputs of this function, of this vector value function. So let's look at this one in particular, and let's just make a table of our t values, x values, y values, z values, right? These components are like x, y, and z, right? So let's write our function again here. Okay, so that's our vector valued function. So let's make a table of values, which I've done already here. You can pause and do it yourself if you like. So when t is equal to -2, okay, my vector is -2, -2, 4. Okay, where is that vector? Where is that point in R3? Let's see, -2 on the x-axis would be here. Okay, then I go -2 on the y-axis, which would be like back here. And then I go up 4, right? So that point would be kind of up here, where this is kind of, okay, that point's got that orientation. All right, now let's graph the next point. Well, it would be -1, -1, 1. So maybe that point would be here, which again, kind of has this orientation. And then my point's at 0. And then 1, 1, 1. Okay. Which would kind of be up here maybe. Let's do these in blue. Spice things up a bit. Boom. 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 My 3D drawing skills are lacking as always. Okay, so I've graphed my points, and what's happening with my curve. It's in 3D space. It's kind of in this back left, or this back octant here. We have octants, not quadrants. And then it's coming forward and going down, and then it's coming back up. And I've kind of drawn this poorly because it should be like coming here. And now it's coming like up out of the screen. Okay, so where this point is like, where is this point? This point is like kind of above. It's like here. And I've even drawn that badly. It's more like here. Okay. So hopefully that gives you an idea of what that curve looks like. So this is one way we can make these curves, which we're going to talk about later. But we see the important point I want to drive home here is that this is just kind of like there's not much to this curve, right? We've seen planes which kind of span, or have a lot more substance to them, right? That they're kind of this big wall of points. And now we've got this vector valued function that's kind of giving us this kind of insubstantial curve. And we could think of this as like a one-dimensional thing, right? Like this curve, it's got a length, I could think about it, it's got a length, but it doesn't have a width or a height, or it's just like a one-dimensional string, I guess you could say. Whereas this, plane, I could think of that as a kind of two-dimensional thing, right? It's got a length going this way and a length going this way. So why do some things in R3 have kind of two dimensions and some things like this have one dimension? We're going to talk about that. Just real quick, some more terminology. This vectored valued function gives us this curve in R3, and the book makes the distinction of calling it a space curve, for whatever reasons. I think the term space is a little unnecessary. It's just a curve. It's a curve in R3. So here we come to the topic I just mentioned. In 12.5 and 12.6, and now in 13.1, we've seen some things, some equations that kind of give us those one-dimensional curves like this in R3, and some of them give us these two-dimensional things like planes. And then in 12.6, we saw even more complicated things like the hyperbolic paraboloid and things like that. Things that were still two-dimensional, right? Like those kind of paraboloids, hyperbolic paraboloids, cones, etc. They still had this kind of two-dimensional thing to them. It was almost like they were blankets draped over an object or something like that. They had, more to them than just a thin line or thin string. So we've seen a bit of both. So why are some things one-dimensional? Why are some things two-dimensional? And the guideline I would give you, if you're a little confused by that, is really look at the number of inputs, the number of variables, but more specifically, the number of inputs, okay, that our equations or functions have. So for example, what we've just been dealing with, these vectored valued functions. How many inputs does this thing actually have? Well, it's only got one input, right? And that input is just it's a number, okay? T. It's just a real number, a single real number input, and then our output is a vector, okay? But this single input gives us kind of a one-dimensional thing in R3. It's just this kind of one-dimensional curve. Where'd I go? Okay. Same thing with what we saw in 12.5. Really, this thing that we saw in 12.5, this equation for a line, this is just another example. This is a vector valued function. Right? This equation of a line, it takes our input t and gives us an output in R3, a bunch of points which form a line. Okay, and again, it's got a single input t, and its output is a vector in R3. On the other hand, we saw these things, which gave us surfaces and planes and etc. So what is this thing? It's a sphere in R3, right? So in particular, this is the sphere with center at the origin and radius 2. So it's kind of like, it's this three-dimensional thing. Or it's a two-dimensional shape, right? Because it's hollow. It's kind of like the skin of a grape, I guess. There's nothing inside of it. It's just this two-dimensional thing. It's living in R3, but it's two-dimensional. And what was this? This was what were these called? Paraboloids. you know, I don't really, I think you guys should memorize the names of all these objects, but I often forget the names. So what does this look like? It's z equals x squared plus 3y squared. So if I take my cross sections, these are parabolas. Okay, so this is kind of like a parabolic object, and then the cross sections are ellipses, right? So this is one of these things that kind of goes up like that. So again, it's got some a little bit more substance than just a line in R3. This is, you know, it's kind of like an infinitely thin thing. You know, we would call it a surface. These are surfaces. So it's got more substance than just a curve. But again, what are the inputs of these things now? How many variables do I see? Well, there are 3 variables here, right? I got my variables are x squared, y squared, and z squared. Now, and then in this equation, I have 3 variables again. I could view this as a function from R2 to R, where my inputs are x and y, and my output is z, right? Okay, so it's got 2 independent variables and 1 dependent variable, and altogether we have 3 variables, right? 3 variables in total. And then this isn't even a function, right? This is, it's an equation for sure. It's not a function because that sphere wouldn't pass any kind of vertical line test or whatever. But again, we have 3 variables. We got x, y, and z, so we have 3 variables. So my advice to you, if you're trying to tell the difference between all this stuff, is look at the number of variables. These curves typically have, they're kind of typically written in this parametric form where we have 1 variable, some real number t. Okay, and that's going to give us this kind of 1-dimensional curve type object. And then these surfaces are typically written with, you know, 3 variables, x, y, and z. And then they give us kind of a 2-dimensional thing living in R3. Okay, so that's my little spiel, and maybe I confused you more than I helped you. If that hurt you, just ignore it, I guess. Now we're going to move on to actually drawing these graphs. So it's pretty straightforward. Don't overthink it too much. There would be two approaches I think you could take that would really start letting you draw these pretty easily. The first we've already seen, just a matter of making tables of values and then plotting the points and connecting the dots essentially. So let's say my function is my vector valued function is given by like this. What should we do? How about t? Let's do t, and let's do something a bit more original. How about t? 3t t squared. Okay. We're going to do some more exotic stuff in a bit. So I should make a table of my t values, and then I plug those into my functions, and from there I'm going to get my components, right? My x, y, and z points or coordinates. Okay. So I have these values, and I can pick whatever t's I want, unless maybe I'm told my t's are between 4 and 0. Maybe not. Okay. So maybe I can pick whatever t's I want. So let's pick t equals -2. Okay. Then my x would be -2, my y would be -6, and my z would be 4. Pick -1, 0, 1, 2. So this is going to be similar to what we have already graphed, but that's fine. Okay. So I get this table of some values, and now I just need to plot them. Okay, so I'm just going to do a quick attempt at this. So I'm plotting my points first, and we can do them in green this time. So at when t equals -2, I'm at, let's see, -2 on the x-axis, -6 on the y-axis. So maybe a point here, and then I'm at 4 on the z-axis. So maybe I'm like here, okay? So that's my point. And then let's see, I draw some more points, you know, at when t equals 0, I'm there. On t equals 1, let's see, where am I? Kind of like here. T equals 2. Here, maybe. Well, I guess it depends on draw it. So it looks like I'm kind of coming this way. Okay, and so this point, for example, would be at 6, 2 on the x-axis, and then 4. Okay, so very similar to what we've already seen. But it's just a matter of plotting points and connecting them. Okay, so that's fairly straightforward. And the more points you plot, the clearer the picture of what's going on. So maybe if you don't draw many points, there's the question of, okay, what's going on between the points? Is it like a straight line, or is it, more curvy in between those points? What's going on? And I think another method you can use that kind of gives you a clearer picture of what's going on is to think about things in 2D first and then add the third dimension. Okay. And this is especially useful, I think, if you see, this isn't the only case when you would use this, for sure. You can use it in a lot more cases. But if you see trig stuff, like when I see something like this, this is kind of the method I use. So what am I going to do? I'm going to look at, let's look at this trig stuff by itself first. And pretend this was in 2 dimensions, okay? This is the x coordinate and this is the y coordinate, right? So if I just had these equations, these parametric equations, and I graph those, what do those parametric equations give me? So let's draw the 3D plane, but then let's kind of confine ourselves to this xy plane for a second. So if I just had sine of t, cosine of t, what equation is that? What figure do I get? Well, if you kind of think back to Calc 2 when you worked in parametric equations, that's going to be the equation of a circle, right? When, let's see, t is 0, well, that's going to be 0. This is going to be 1. And then when we go to pi over 2, so let's see, so when t is 0, I'd be, where would I be? 0x, 1y. So I'd be like here, okay? And then when t gets to pi over 2, I would be here. And then t gets to pi, I'd be there. And 3 pi over 2, I'd be here. Basically, if I just graphed those 2 components, what I would get is a circle. Okay. But that's just those 2 components. What's happening to the z components, right? So what I've drawn here, the z component for all those points is 0. But it's not 0 in our original equation. Okay. So as t increases, my z coordinate should be increasing. Okay. So yeah, maybe at when t equals 0, I would still be there, right? Because my function is sine cosine t. But then when t equals 1, well, I'd be here kind of in the xy plane, but I'd be up 1 in the z plane. So I'd be here. And then when t equals, wow, no, I'd be up pi over 2, right? Further. Right. So when t is pi, where would I be? Well, I'd be at this point, I'd be on the axis horizontally, but then I'd be up a distance of pi. And when t is pi over 3 pi over 2, okay, I'd be kind of at this point on this axis in the xy plane, but then I'd be up by 3 pi over 2. So I'm still in the xy plane, I'm still kind of making these circles, but then my z coordinate is increasing. So what I end up with is a spiral. That kind of spirals around the z-axis. Okay. So I've drawn this poorly. Kind of gives the impression that these spirals are getting narrower, which is not the case. So if I looked straight down, so this is a spiral or kind of like a helix going upwards. So if I looked straight down at it along the z-axis, what would it look like from above? It would just look like a circle, right? But then if I kind of backed away and looked at the full view, I see, well, it's not a circle, it's this spiral that's going up and up and up. Okay. So I think this is a useful trick, kind of confining yourself to 2 dimensions and then looking at what's happening in that 3rd dimension and like stretching or compressing out your thing as necessary. What I kind of think of is like, I kind of picture this in particular as like almost like a slinky, right? So when you, if you only look at like the 2 dimensions of it, it's just kind of like a circle, right? If like you kind of squash your slinky flat, it'd be just a circle, right? But then you look at that 3rd component and you say to yourself, what's happening with this 3rd component? Well, I'm kind of stretching my slinky upwards, right? So it's like you pull on the top of your slinky and stretch it upwards. And what happens to that slinky? It becomes like a spiral, right? So that is kind of how I approach some of these problems. And I think that's a useful technique to be able to utilize. Now, let's talk about this situation where we're given, maybe I'm given a graph or I'm given a couple equations and I'm told to find a vector valued function that kind of represents a curve, a particular curve. So an example of what I'm talking about, if you look in your ebook, example 5. Example 5, I'm not going to go over because that's exactly what we've done in section 12.5, I believe, finding the equation of a line segment between 2 points. We've done that before. So review that material. More interesting would be example 6. And then there's, I'm looking at your homework, and there's a couple problems in your homework that deal with the same topic. So I'm going to give you some general guidelines on how to solve these problems. And let's start with one of the homework problems first. Let's start with number 17 in your homework. That's a good example. And then number 16 is similar, but number 16 is a bit harder. So let's, it kind of walks you through it a bit more. But let's start with 17. So 17 is an example of one that's not too difficult. I'm given two equations. Okay. So, and the problem is, okay, find RT that represents the intersection of these two surfaces. So what's going on? These equations give me surfaces in R3. Okay, what is y equals 2x squared? Just a quick sketch. Uh, the picture is not going to help us too much. It might just kind of give us an idea of what this problem is asking. Y equals 2x squared. Well, that would be, that's a cylinder. In not a circular cylinder, but remember 12(6), our kind of general definition of a cylinder. So y equals 2x squared. Okay. Well, if I just was looking in the xy plane, that'd be a parabola, right? That looks like that. But since in R3, this is actually a whole surface, right? So this is kind of this 3D surface like that. And then what's z equals 5x squared plus y squared? Well, that would be, kind of a, what do they call them? A paraboloid. It's kind of like a cone, but the cross sections are parabolas. So let's see, z equals 5x squared. Well, that would be the parabola going this way, right? And then z equals y squared would be a parabola going this way. And then the cross sections would be ellipses. So this is kind of like an ellipse. And we can tell there'd be some sort of intersection with, they'd intersect each other. And it looks like, if you can picture it, it looks like the intersection would probably be, it would look something like this. It'd kind of be like a segment of a parabola. It'd kind of look like this. Okay. So the problem is asking, okay, how do we find the equation of that thing? Okay, which is a bit complicated, right? I don't know. Looking at that, that doesn't remind me of any particular equations. So it would be hard to find an equation for that by itself. So to find the equation for that, what we really need to do is look at these two things and try and get some vector valued equation from these two. Okay, so how do we do that? Well, this intersection it's the points x, y, and z, or the vectors x, y, z that make both of these equations simultaneously true. Okay. So both of these equations have to hold for my t values. I'm looking for something like this. Okay. So I'm looking for some equations, f of t, g of t, h of t, and let's see, I want to be able to plug t values into this thing and get x, y's, and z's. And then if I take those x, y's, and z's and plug them into both of these equations, both equations should be true. Okay, so that's kind of what's going on. Now, that's the idea of what's going on. The mechanics of it are a bit simpler, I think. So what are the mechanics for finding these functions? What I'm going to do is I'm going to pick one function and solve for I'm going to pick one function to start with, one of these, or I should say equations. I'm going to pick one of these equations. And let's pick something, let's start by picking something simple. Okay, so this one on the right's a bit more simple, right? It's only got y and x. It doesn't even have a z, right? So it's a bit more simple. So I have this, I've picked this simple function. What do I do for that simple thing? What I'm going to do, I'm looking at this equation on the right side. I got a y and I got an x. I'm going to pick one of them to be equal to t. Okay. So let's say x equals t. Why did I pick x? Because if x equals t, I plug t into there, right? And then y is just going to be equal to whatever this right side is, okay? So y is going to be equal to 2t squared. Okay, pretty simple. That was pretty easy to find, right? If I had done it the other way, you know, it'd be a bit uglier. If I'd said, okay, y equals t, then x would be equal to t over 2 square root, and that only works if t is positive, etc. So I want to do it this way. Okay, now I know x and y in terms of t. And then this equation over here tells me z in terms of x and y. So what I'm going to do is I'm going to take these values for x and y, and I am going to plug them in for my z equation. Okay, so I can rewrite that equation as what? Z equals 5x squared, so 5t squared, plus y squared. Well, what's y squared? That would be 2 squared squared. So z equals 5t squared plus, I'm just simplifying this. Plus 4t to the fourth. And that should be it. I guess we'll never know if that's the answer though, because my internet cut out and say, well, this should be an equal sign for sure. That should be a plus. But I guess we'll just have to hope. All right, so now let's see an example like example 6 in the textbook or number 16 in the homework. I'm going to do one from the textbook though. Okay, so let's look at, what's a good one? I think 45 would be good, number 45. So let's look at the intersection of these two curves. Okay, the setup is the same as previous example. We have these, or they're not curves, they're surfaces. Let's look at we have two surfaces in R3, right? And we want to find their intersection. So let's see, what does this look like? It's a circular cylinder. Okay, that goes down forever, up forever. And then what is this thing on the left? I believe that's going to be one of those hyperbolic paraboloids, right? So kind of one of those saddle shapes, which I don't want to draw. Okay, we can find these intersections without drawing them, okay? Like 45 doesn't even give us pictures or anything. It just says find the equation of the intersection. So I still want to find some vector valued function like this. And I want to find my f of t, g of t, h of t. Now this example is a bit harder because there's not really any really super easy starting point. Like in the previous example, let's see, we just looked at this right side and we say, okay, x is equal to t, then that makes y equal to 2t squared and so on. Okay, so that was pretty straightforward. In this, we can't really do that. I can't, so you might be thinking, well, why don't you let z equal t? Okay, well, I don't want to do that because I kind of want to start in an equation that only has two variables, okay? So I really want to start on this side, because if I start on this side and I plug t in for z, right? Okay, well, I'm never going to be able to solve for x and y in terms of t, okay? It would just be complicated. And so I want to start on this right side. I want to plug some function of t in here, okay? So what do I do? Well, what function of t would fit in this right equations? What functions of t would fit in this right equation and make this equal to 1? When you see x squared plus y squared equals 1, or x squared plus y squared equals blah, blah, blah in these problems on this homework, and in general, whenever you see an equation like this, you should think to yourself, well, if I need to, I can make some some trig style substitutions. If I said x is equal to sine of t, right? Or how about let's do this. X equals cosine of t. How about that? And y equals sine of t. I like that a bit better. Well then, x squared plus y squared equals 1. That's the same as cosine of t plus sine of, or cosine squared of t plus sine squared of t equals 1, right? And this equation always holds. It holds no matter what t is, all right? So if x is equal to cosine and y is equal to sine, okay, those functions will work for this right side. Okay, but I also want them to work for my left side. Okay. And do they? Okay. Well, as long as I let z, well, I don't even have to solve for z, right? Because this left equation gives me z in terms of x and y, x squared and y squared. So if I know what x squared and y squared are, I automatically know what z is. Okay, so I have my three equations. Okay, so my function r of t must be equal to cosine of t, sine of t, and then cosine squared minus sine squared. Okay, so I get this, and let's see. We picked x equals to cosine and y equals to sine, but we could have done just as easily done the reverse. We could have said x is equal to sine of t and y equals cosine of t. And then this z would be sine squared minus cosine squared. So either one of those should be acceptable. So let's see if the book agrees. What number did we say? 45. It does, but the book uses the identity. The book writes cosine instead of cosine squared minus sine squared. This is the same as cosine 2t. So the book writes this solution as see exactly how they write it. Yeah, they write it as cosine t sine of t cosine 2t. That's also acceptable, but I mean, this is also acceptable. cosine squared minus sine squared would also be acceptable. And the book also writes it in this IJK notation. They write cosine t I plus sine of t j plus cosine 2t. Okay. Again, that would be acceptable, and maybe your WebAssign wants you to enter it like that. So the punchline is, if you see x squared plus y squared, something similar, keep in mind that, okay, if you make some trig style substitution using the identity cosine squared plus sine squared equals 1, that might be the simplest way to do things. So keep that in mind.